All right, let's go ahead. So welcome everyone. We are in a new seminar of the Commission G5 of the IAU talks on the topics of the Commission, which is stellar and planetary atmospheres. Today we have the pleasure to have as a speaker Robin Baeyens from the University of Amsterdam, who will talk about photochemistry and chemical inhomogeneity on hot giant exoplanets. He did his bachelor in physics, a master and a PhD in astronomy at the Catholic University in Leuven. He was the recipient of the Odyssea Prize, Paul Schmeyer's Prize awards for his work on his master's thesis. And his research is mainly focused on exoplanets, on the structure and the chemistry of exoplanet atmospheres. So welcome, Robin, and the floor is yours.
Okay, thank you, Carlos, for the nice introduction. And thank you also for giving me the opportunity to present. So the topic that I would like to talk about is indeed photochemistry and also chemical inhomogeneity in the atmospheres of hot giant exoplanets. And the main idea that I want to convey, so I will already say it up front, is that we cannot neglect photochemistry anymore now that we have the great data from James Webb Space Telescope, but I will show you immediately. So this is a paper that we've published quite recently, and you can see some of the collaborators here. So I would like to start by mentioning this planet. It's WASP-39b, and it's a kind of already quite famous planet because it was it's a hot gas giant transiting its host star, and it's one of the first planets that the James Webb Space Telescope has observed. And here you can see the spectrum of this planet. So it's a near-infrared spectrum, and what you can see is that there is some hints of water that we can observe. There is also this nice bump, this huge bump, which corresponds to CO2 absorption in the atmosphere of WASP-39b. And this is really the first time that we've seen CO2 with such clear significance. So this is I believe a 26 sigma significant signal. So it's never seen before like that. But what is even more interesting is that here around 4 micron, there is this kind of unknown bump, or at the time it was unknown. So there's a kind of absorption where the transit depth is higher. So that means absorption by some molecule in the atmosphere. So what was done is that, of course, it was attempted to figure out what kind of molecule could cause this signal. And here it was found that this is SO2, so sulfur dioxide. And it's a very nice result because it's the first time that sulfur dioxide was observed in any kind of exoplanet atmosphere. It's also actually the first time that any sulfur species was observed in an exoplanet atmosphere. So it's great because it unlocks a new element that can tell you about the atmosphere. And why it's even more interesting is that sulfur dioxide can only be produced in this kind of atmosphere via photochemistry. So it's the first, really the unambiguous detection of photochemistry occurring in the atmospheres of other planets or exoplanets. And here you can see a new figure where really a photochemical model, so a more dedicated model, was used. And you can see that it really nicely fits both the SO2 and the CO2 absorption features. In the meantime, there's also WASP-107b, that had its atmosphere observed, and also SO2 was found in this planet. So right now we have already several planets where this SO2 was discovered. And this is really probably going to grow in the future as well. So I need to tell you maybe a little bit why all of this is exciting. So why do we want to know what the chemistry or the photochemistry of extrasolar planets is like? And I have three main reasons for this. So the first is that the chemistry is really a crucial part of the atmospheric system as a whole. And it has very important feedback mechanisms to the radiation and also to the temperature in the atmosphere. So it's really one of the main parts that we need to understand to be able to really say something about the atmospheres of these planets. The photochemistry, of course, links to the host star because its photochemistry is caused by mainly UV radiation coming from the host star. And as we have seen, it's also important to understand the observations that we are now getting from exoplanets. Secondly, what is also important is that understanding the chemical composition of a planet or the bulk chemical composition, it tells you something about how this planet was formed. And especially the elemental ratios are here very important, such as the carbon to oxygen ratio or carbon to sulfur ratio, because these elemental ratios, they trace different locations in the protoplanetary disk. And they say something about the kind of gas that was accreted by the planet during the formation stage. So it's really important to know what the planets are made of to basically be able to say something about how they are made and how planet formation in general is working. And finally, a topic that is also quite important is, of course, that it says something about biosignatures. The chemical species in the atmosphere could be biosignatures, or they could be false positives for biosignatures. And photochemistry is a very important source or sink for these kind of species. So also quite recent research has shown that, for example, biogenic molecules such as DMS, so dimethyl sulfide, hints of these species have been found in some water-rich exoplanets. And now we need to basically understand how they interact with the chemistry and also the photochemistry to know how much of a robust biomarker these sulfur species could be. And of course, there's also the ozone, which is a bit more close to what we know from the Earth's atmosphere, which is a very important photochemical species that has to do with the oxygen and with life. So I think plenty of reasons to be excited about this kind of research, I hope. And here I want to introduce to you something like three classical regimes of three chemical regimes of exoplanet chemistry. So here I have a graph which shows the molar fraction, so the amount of some chemical element in the atmosphere as a function of pressure on the vertical axis. And pressure on the vertical axis is actually also the height in the atmosphere. So the low pressure is, of course, high in the atmosphere. And I will be mainly talking about the atmospheres of hot Jupiters. So you have, of course, a lot of hydrogen and helium. And then some of the other dominant species here can be CO, water. You could also have, if the temperature is right, you could have methane and ammonia. And the solid colored lines here are from a dedicated photochemical model. So we calculate the photochemical kinetics and the reaction rates of all the reactions that we think are occurring in the atmosphere. And the dashed lines, they are from a chemical equilibrium model. So that means basically if we minimize the Gibbs free energy and we have the then we have the concentrations as they would be in chemical equilibrium. And you can see that in the deeper parts of the atmosphere, chemical equilibrium is a reality. So the That means that the chemical reactions occur very quickly. The temperatures and the pressures are also high, so the chemicals timescales are very short, and the composition of most species are close to its chemical equilibrium. However, if you go up in the atmosphere, you enter in a more dynamical regime where you could see, for example, vertical mixing. So that means that the mixing is fast enough and the chemical reactions cannot occur quickly enough to bring the composition to its equilibrium state. And basically the chemical concentrations are frozen out. They remain constant as a function of altitude because the mixing is so fast and everything becomes more homogeneous. And then finally, you also have an upper layer in the atmosphere where the photochemistry becomes more important. And there you mainly see dissociation of species, such as, for example, the methane and the ammonia here is very clearly dissociated by the UV radiation from the star. And this is kind of a big picture schematic of what we expect the chemical or the chemical regimes in our Jupiter to look like. Now, interestingly, if you have dissociation in the atmosphere, for example, here ammonia and methane, they get dissociated. That means that hydrogen atoms are loose or are freed from the molecule, and the carbon and the nitrogen, they become available to have new reactions with, and then you could have species such as hydrogen cyanide forming. So this is mainly produced via photochemistry. I already gave the example of sulfur dioxide in WASP 39b. So this is made primarily from hydrogen sulfide, where the hydrogen is freed and the sulfur can go into sulfur dioxide. So this is basically how it works. So you can see it here. If we have some dedicated photochemical kinetics models, we can have some prominent species forming via photochemistry via these net reactions that you see here. So HCN mostly draws from a reservoir of methane and ammonia. We also have acetylene, that's C2H2, that draws from a reservoir of methane, and the SO2 draws from a reservoir of hydrogen sulfide mainly. And these are net reactions, so there are multiple steps, but in each of these, one of the steps is caused by a photon hitting one of the molecules and the species dissociating. So here you can see it in a little bit more graphical way. So you start out with hydrogen sulfide, that's H2S, and actually it's not the interaction of hydrogen sulfide with a photon that removes the hydrogen atoms, but it's actually the water. So you have H2O, which is split into H and OH, and these two radicals, they interact with the hydrogen sulfide and they can strip off the hydrogen atoms such that in the end sulfur dioxide can form. So this is a little bit generally how it goes from a molecule which is more hydrogen or hydrogenated actually to a molecule that is a little bit different. And in the end, this can actually lead to more complex chemistry. So in the end, you can also form photochemical hazes where longer and longer carbon chains or sulfur chains can form, and they really become macroscopic molecules that can be observed. So of course, there's a big effect in that is caused by temperature and also the UV radiation from the star. And in a previous work, we modeled a grid of several different planets ranging from cool to hot. And I showed 3 of these models here to basically see where photochemistry could be the most important. And it's actually a sweet spot between the cool and the hot case, because if you have a look at the cool planetary case, then this means that if the planet is cool, it's further away from the star. So it means that also the UV radiation received from the star will be a little bit lower. And that means that, of course, lower UV radiation, lower photodissociation rates, and the atmosphere is mainly dominated by the dynamical processes. On the other hand, in the hot case, where the planet is very close to the star, the UV dissociation is quite strong, but the planet is also quite hot. So chemical reactions happen quickly, and the planet tends to be more in chemical equilibrium. And we have lower concentrations of these specific photochemically produced species, such as acetylene or HCN. And it's really in the middle that you have a sweet spot where you do get strong enough photolysis, and you have still a reservoir of parent species where you can form, for example, acetylene and HCN. And in this case, the middle ground is actually an equilibrium temperature of about 1200 Kelvin. And this is also the same ballpark temperature as WASP 39b, so where the first photochemical evidence was found. So this is all nice and consistent. However, there's also hotter planets, and they're also quite interesting, as I will show in the rest of the talk, where I will go to the really much hotter, so we call these the ultra-hot Jupiters. They are a little bit of a distinct class of exoplanets. But my main point will be that even in these planets, photochemistry could be important. So why are they a little bit of a distinct class of planets? Well, for ultra-hot Jupiters, they start to get emission features in their spectra. So here you can see a more statistical study of several hot transiting exoplanets, so hot gas giants, ordered via their equilibrium temperature. And at some point, we see that the deviation from a black body that was measured, it goes up. So here it was basically a ratio between the data points inside a CO absorption band and outside CO absorption band. So if it here goes up, that means that there's a CO feature that can be seen in emission rather than in absorption. So that means that there is somewhere in the atmosphere a thermal inversion occurring. So that's because there's this strong radiation on the day side of this planet. Furthermore, many of these planets have high enough temperatures to have metal evaporation in their atmosphere. So for many of these planets with high resolution spectroscopy studies, metal atoms or metal ions even have been detected. And this is really a testament to basically how hot they are. So they're going over over 2000 or 3000 Kelvin even. So slowly going towards the region of or towards the temperature regime of stars even. And from these metal concentrations, you can also say stuff about the interiors of these planets. We are also entering the region where you will not find molecules anymore, because at some point the atmosphere will be too hot for molecules to exist, and then you enter the regime of thermal dissociation. So here you can see a schematic that shows that depending on the gravity of the planet, roughly if you go over the 2500 to 3000 Kelvin mark on the day side, then most of the water actually will be dissociated. So there you have the H2O, which splits into H or OH and OH. And then finally, it's also an interesting playground actually for 3D studies, because lots of these planets, they are tidally locked, so they have a permanent day side and a permanent night side. The day side is completely blasted by the star, but the night side is not, it's shielded. So there can be quite drastic temperature differences between the two. And this could also lead to condensation on the night side or even a cold trap, which is what you see here on the lower figure, where in the atmosphere of the planet WASP 76b, there were many detections of metals, and if you order these metals according to their condensation temperature, you see that after a while, for the high condensation temperatures, the detections stop, or because these metals are not present in the atmosphere anymore, or because we cannot see them. So that means that for the most refractory species, you actually lose these species. So this could be an indication of a cold trap where maybe they are evaporated on the day side, but if they are transported to the night side, where the temperature is lower, they condensate and they are removed from the atmosphere, something like that. So it's really a very exotic environment. And in this exotic environment, we are going to talk about chemistry, because I will focus now on this planet, WASP 76b. It's an ultra-hot Jupiter transiting an F-type star in a very short orbit. And because of this, the temperature, or the equilibrium temperature of the planet, is 2200 Kelvin. Why do I want to talk about this star specifically, about this planet specifically? That is because there was a detection on this planet of HCN, and more specifically, the detection was on one of the limbs of the planet. So basically on one side of the planet, but not on the other. So here you can see the viewing geometry. So if the planet is transiting, we are actually the observers on the bottom of this figure here. And on the right side of the planet, there was this HCN absorption signal. On the left side of the planet, there was no such signal. So that's kind of weird. They also found that the signal was a little bit redshifted. So it would mean that the air in the atmosphere is moving from the night side to the day side. So quite interesting detection, especially because the planet is in principle too hot for HCN to occur there without having a very kind of exotic composition. So this begs two main questions. The first is, how is the HCN formed on the ultra-hot planet like that? And the second question is, what is causing this asymmetry in the signal? We tried to figure out this kind of mystery by making atmospheric models. So we basically combined two main models to arrive at a picture of the atmosphere. The first one we use is a 3D GCM. So this is basically a 3D climate model where we model the irradiation from the star on the atmosphere, and then we have the whole climate with the winds surrounding the planet and how the heat is redistributed, etc. And then we use this temperature and wind information in a chemistry model to basically compute what we think would be the chemical composition on this planet. And our chemistry model is a photochemical model that can take into account photochemistry, of course, but also vertical mixing and also advection from the day side to the night side of the planet. So here are the results for the 3D GCM first. So this is actually a previously published model for this planet by the expert MIT GCM. And what you can see is that the day side here is very much hot. So the overall temperature is around 3000 Kelvin. The night side is much cooler. There, the temperature goes to 1000 or even below 1000 Kelvin. And you also see a kind of the pressures or like the altitude in the atmosphere indicated. And one of the outcomes also of the climate model is the wind, as I said. And the wind is mostly manifested as a super rotating wind jet. So this is a very fast wind jet that is super rotating. So that means it is faster than the rotation of the planet. And it goes around the equator in this kind of, on this figure, in this anti-clockwise direction. And this is really a quite common or robust outcome of these hot Jupiter climate models, that we have this super rotating wind. And we see it in many other kind of planets, not only in the very hot ones. And there's also been observational evidence for such wind jet. So this is in itself not very surprising, but it's kind of interesting because it provides this link, this advection between the day side and the night side. And what we did next is use this temperature and wind information in our chemistry model. And here I show the concentrations of two of the most dominant molecules, that's N2 and CO. And what we can see is that there's quite a uniform abundance of N2 and CO, except in the day side, in the upper part of the atmosphere. There you can see that N2 and CO, they are dissociated. So they're really, the temperatures and also the UV environment there is too extreme for these molecules to exist, and they are dissociated. They fall apart into their constituent atoms. On the night side, on the other hand, you see that most of it is already recombined again. And there, because of the temperature, which is lower, these molecules can still exist. But this is actually quite interesting. So we look at the atomic composition now, and we see that this is a little bit of the negative version of the previous figure, where we have an atomic nitrogen and carbon composition on the day side. We also see some on the night side in the very most upper layers. So we really have now the situation where on the day side, there's molecular dissociation, and this atomic composition, it gets transported via the wind jet towards the night side. I should also mention that I did not choose N2 and CO to show by accident. These are actually the most stable molecules. They have a strong triple bond, so they are chemically quite stable. And even these species are dissociated. So that means that most of, or almost all other molecules will also be dissociated into the atomic forms. And what happens now when these atoms, they are transported to the night side, they are carried into a regime where the temperature is much lower, where the UV radiation falls away because it's shielded, of course. And there it can do new chemical reactions. And what we see, if we look at HCN concentration, we see that there is this nice kind of asymmetric, asymmetric concentration that we see building up on the night side that is caused by these atoms that are carried from the day side and that can basically recombine and form HCN. This recombination takes some time, and the time that we see is really the effect, or what we see is really the effect of that time, because we have on the evening limb, so the left side of the figure here, we have a low HCN concentration, but as the wind is carrying the gas around the planet, so across the night side, we have the HCN concentration, which is building up and increasing until you get to the morning limb of the planet, where you get the maximal HCN concentration. And then if you cross again into the day side, then of course, everything will be destroyed again. So we were actually quite pleased to see that, because this is a nice proof of concept for this kind of asymmetric HCN signal that was detected for this planet. So very nice. Now, one of the important points, okay, so these are the chemical pathways. I will skip it. One of the important points to stress is that photochemistry is a very important and even a necessary step for HCN to be present on the night side. And that sounds a little bit paradoxical because photochemistry is a process that occurs on the day side. But if you compare our result with a model where we left out photochemistry, then you see that in the model without photochemistry here on the left, CO remains stable and constant everywhere in the atmosphere. So it's impossible to destroy CO, and it's impossible to free up carbon, the necessary carbon for the HCN to form on the night side. So this is really a strict condition that we have. It's the photochemistry that we add in our model that is doing the extra dissociation of CO, and that's freeing up the carbon for the HCN on the night side. So this is really important because that means that you cannot neglect this kind of effect in the interpretation of observations. Of course, it's not only the photochemistry, but it's also the wind advection that is taken into play here. And we try to have a look at what is the effect of the wind advection. So we varied the wind speed of this equatorial wind jet, and we made different models of that. And here you can see the HCN concentration as a function of longitude. So here 0 degrees is the middle of the day side, the substellar point. And if you go to the higher longitudes, at some point we go across the evening limb. So first, the HCN concentration is low in all of the models. But if you cross the evening limb on the night side, then the HCN concentration can start building up. And it builds up as you go further across the night side, and then you reach the morning limb again, and then it drops down again because the day side was reached. And these different models, they correspond to different wind speeds of the equatorial jet. And in the darker colored, you have the slowest wind. So you see that in the end, it's because it, in the darker color, it's the fastest wind. It's the fastest wind speed. It's 11.7 kilometers per second. So because the wind is carrying the gas so quickly across the night side, the chemical reactions do not have enough time for the HCN concentration to build up. And if the wind jets get slower and slower, we see that there's every time there's more time left for HCN to build up. And in the end, the slowest wind jet saturates even a little bit, and we get our maximal HCN signal or HCN concentration for the slowest wind jet configurations on the morning limb of the planet. So it's really nice to see also this interplay between the advection, the dynamical regime of the planet, and the chemical regimes of the planet. So these two timescales are very important. We also took a look at the sulfur chemistry on this planet, which is, of course, very topical with the SO2 detection that is now being made possible by the James Webb Space Telescope. And for sulfur, we see kind of a similar effect as for HCN. So we looked here at two species, S2 and SO2. Especially for SO2 on the bottom, you can see that there's this kind of similar asymmetric concentration. So this tail that is building up with a maximum near the morning limb of the planet. And that's really, it's a very similar mechanism. So you have the radicals that are necessary, and on the night side, the temperatures are lower, and the species can be built up. However, here we verified also the effect of photochemistry in itself, and we found that photochemistry is not actually necessary to produce this. So if we have the model without photochemistry, it produces the same picture for the sulfur species, and that is because the SO2 especially, but also S2 it's being driven by the dissociation of water, not the dissociation of CO. And water is always dissociated in our model, even if we don't include photochemistry, because the temperatures are just are already high enough. So thermal dissociation provides enough radicals of the water to kickstart this sulfur chemistry. And then finally, we also had a look at what we weren't able to do, because the models that I just discussed, they are the climate model and the chemistry model, but we modeled one after the other, so they don't communicate with each other, and it's not necessarily self-consistent. In principle, the chemistry would have a feedback on the temperature again, and you would be able to reach a convergence by iterating them, but we did not do that. So if we would have a self-consistent situation, then that maybe would lead to a thermosphere forming or an ionosphere forming. And that is what you can see here. And you can also see the effect of photochemistry here. So what we did was we took a temperature profile, and in the upper part of the atmosphere, we used two different assumptions. First, a cool assumption, where we just have an isothermal upper atmosphere, and otherwise a hot assumption, where we assume that we are reaching levels at which we are reaching into the thermosphere, and the temperature rises to about 10,000 Kelvin. And for these two assumptions, we tried out the chemical model, and we can see here in the abundances of CO and N2 that if you have the cool assumption and you neglect photochemistry, you see that they are constant, so they don't get dissociated whatsoever. If you have the hot assumption, then they do get dissociated in the end. So there will be a pressure at which these species are destroyed, and it's mostly when the temperature reaches over about 3,000 or 4,000 Kelvin. But if you also take into account photochemistry in that regard, then you see that the pressures are much higher, and that the dissociation also already begins at much higher pressures. And this is, of course, the point that I already stressed, that the photodissociation is extremely important here in setting this boundary between a molecular and an atomic transition in the atmosphere. If we were to have a self-consistent model, this would also have a great impact on the temperature itself. So because if you dissociate molecules, you remove actually the molecular coolants, the atmosphere will probably stay hot, and it will be an early rise of a deep thermosphere or a deep ionosphere. So this strong chemical and thermal feedback is something that we would like to include in the future. We also thought about the ions, actually, because we now computed neutral chemistry. In the future, we might want to do also neutral ion chemistry to see what the effect of that would be. And potential ions that could be present are this HCN H+, so it's HCN with a proton added, or H3+. For the positive ions, but maybe it's more realistic to expect negative ions, because there's also the metals that I already mentioned. They tend to be ionized, so that gives a big reservoir of free electrons. And then you could maybe have more the negative ions like Cn- or H-. H- was already detected on some planets that have very high temperatures, but not on this one. So that's a kind of way that we would like to have in the future. So I will present some of the take-home messages that I try to weave already a little bit into the presentation. So mostly, despite their high temperature, the photochemical disequilibrium and the photochemistry especially still applies to this ultra-hot Jupiter. So we cannot just say, oh, they are very hot planets. We can just assume that they are in chemical equilibrium. So that's impossible. the CO and the N2 can be dissociated, even though they have this strong even though they are the strong triple bonded molecules. And it is because you have this combination between thermal and also photodissociation. We found that the day side dissociation in combination with the horizontal transport is actually an interesting proof of concept for this asymmetric HCN signal in WASP-76b. We say that it's a proof of concept because we found in our models that there's quite some sensitivity to assumptions, for example, with the wind speed, with the temperature, with the upper atmosphere, etc. So it's like a proof of concept, but in order to really explain the signal, a more dedicated study would probably be needed to, should be done. And then finally, this photochemistry and photoionization, it really changes the atmospheric structure. It can even change the atmospheric structure on the night side, which is a little bit of a paradox because there's photo in the name. So it comes from the radiation from the star, from the light from the star. But even via this advection on the night side, it cannot be neglected. So these ultra-hot Jupiters, they are really a nice laboratory for molecular recombination, ionization, condensation processes, or to look for asymmetries, which I expect will be published in the future as well. I think as the techniques that we use to observe exoplanet atmospheres mature, we hopefully will see more of these studies on asymmetry between the two sides of the planet. And to finish off, I would like to have like a very short look into the future for WASP-76b, because in the previous cycles, James Webb was a little bit neglecting this interesting planet, but now, luckily for the current cycle, there will be 3 programs on this planet, one by me, which is of course very fun. We will have a nearest transit, so in the near infrared. We will have a MIRI transit, which is in the further infrared, where we can also study clouds and condensation processes on the night side. And there will also be a phase curve. So this is when we observe the planet as it goes for a full orbit around the star. So this really gives a good handle on how the heat, the temperature, and how the chemical species are distributed along the planetary atmosphere. And I also want to make a little bit of an advertisement. So I already mentioned the ions. This is something that we are very interested in, and we are leading a workshop now on the neutral and ion photochemistry of planetary atmospheres, where the main goal would be to combine insights from, on the one hand, exoplanet photochemistry, but also solar system photochemistry, and also lab studies on photochemical experiments and chemical data. So I think it would be very nice. If you are interested, you can just contact me or one of the other organizers. There are still some spots left for this workshop, which will happen next summer or this summer. And with that, I would like to thank you for your attention. Yeah, if there are any questions, please let me know.
Robin, thank you very much. Thank you very much for a very nice talk. And it was really visible very well how complex the planetary atmospheres are. So now we have time for questions. So please your hand if you have a question.
There is already...
There is one in the chat, yeah.
Yeah. One is, somebody is asking, what is the difference between equilibrium temperature and photospheric temperature, and how this temperature is estimated observationally?
Right. So yeah, there are different definitions for the temperature that I used during my presentation, and I didn't explain them. So I apologize for that, but I will make up for it. So the equilibrium temperature is a parameter, or is a kind of quantity that we use often for planets to have just a bulk estimate of what the temperature could be. So it's really computed in the way that we look at how much energy from the star is intercepted by the planet and how much energy is radiated again. And then we assume that this is in a balance, so in an equilibrium, and we calculate the temperature based on that. So, for example, for the planet WASP-76b that I talked about, the equilibrium temperature like that would be 2200 Kelvin. Important to note, and I think that was also clear from the climate model, is that this does not reflect the actual temperature or the photospheric temperature or the temperature of the planetary atmosphere. There we can have very strong local differences, and you could see that the night side was much hotter than this 2200 Kelvin, and the day side was the night side was much cooler. So we had like a 3000 Kelvin night side, or 3000 Kelvin day side, sorry, and 1000 Kelvin night side. So the local differences, they are really the temperature, like as a physical concept, and this equilibrium temperature is more of a calculation that we do based on the energy that the planet receives from the star.
So somebody else? Okay, Nicola Vitas, please.
Thank you for the very nice talk, Robin. It was very inspirational, and I would just like to ask you one thing. So these equilibrium processes are a big issue also in the modeling of brown dwarfs. And in brown dwarfs, if it's not a binary system, you don't have a star illuminating the planet, and the temperatures are about the same in the ultra cool objects as the ones that you find in this hot Jupiter, so around between 1000 and 2000 kelvins. So are there processes that you consider to drive the chemistry out of equilibrium other than just the photochemistry and the interaction between the radiation and the molecules?
Yes, definitely. So the vertical mixing, so that's in the very beginning of the talk, if you remember, where I highlighted the three regimes. The photochemistry is really driving the disequilibrium in the upper atmosphere, and in the middle part of these three regimes, there you have vertical mixing, which is extremely important in driving the disequilibrium. And I think also in brown dwarfs, vertical mixing is quite a big issue, or like quite an important process. So this is really the dynamics of the atmosphere that are acting on a time scale that is shorter than the chemical time scale, and it really changes the chemical concentrations of molecules and chemical species quite a lot. So we take this into account in the model as well, but it's via a parameter called KZZ, and this parameter is quite ill-constrained, so there's also assumptions going into that kind of approach.
Okay, so in a way, I mean, the disequilibrium on the dark side, on the night side of your planet could be driven. I mean, it's not such a surprise that there is also some disequilibrium on the other side. It could be due to the vertical mixing, no?
Yes, yeah, vertical mixing definitely comes into play as well, and it changes also the concentrations of, for example, the HCN that we saw is also changed by vertical mixing, because there's this particular layer where the HCN formation on the night side is very efficient. And if the vertical mixing is low, that means that the HCN remains quite confined to that layer. But if you have, for example, very strong vertical mixing, that means that most of the night side will start to be we start to be enriched with this HCN, because it can be moved from the layer where it is produced, and it can be transported upwards and downwards. So this is also, this comes into play as well.
Perfect. Thank you very much for the answer.
Okay, Carlos, please.
Just a curiosity. Well, first of all, thank you very much for the talk that I found really very well explained. A lot of complex concepts. And one question I have is of course, you coupling here the radiation field of the star now with the structure of the planet, and the thing that I would perhaps worry about is that the most important part of the UV of the radiation field from the star is the UV. And while model atmospheres are pretty reliable for the photosphere, which gives the optical range for cool stars, the UV part comes normally from higher layers in the stars that are much harder to model and are quite uncertain. I didn't get an impression, a feeling from your talk of how the uncertainty in the UV radiation field from the star would impact your photochemistry models.
Yeah, I totally understand the concern, and I have it as well, because for many of the exoplanet hosts that we are interested in, we don't really have a great handle on the UV radiation, so there may not be observations, or it's usually a combination of observations and models that we would like to use there. So we work sometimes with proxy stars, where we say, okay, these stars are kind of similar, so we hope that the UV wavelength range is also a little bit similar. And that introduces uncertainties for sure. So I think in this case, we did not do a sensitivity study on the UV radiation. In my opinion, I don't think it matters that much in this specific case, because what the UV radiation is doing in this mechanism that I presented is it destroys the CO2, or it destroys the N2. So the amount that we get is not extremely important. It's just important that we have this photodissociation mechanism in the model, so that we have the reservoir of atomic radical species that can be affected to the night side. And for the HCN formation, it doesn't really matter, because there the UV the UV doesn't reach the night side, of course, so the exact rates for the HCN formation will not change that much. However, if you are looking at, for example, the WASP-39b, where the SO2 signal was discovered, there is some sensitivity to the UV radiation, and if this changes, then you expect a higher or a lower abundance of SO2. So there's indeed some uncertainty in that, not in this specific case, but in general, that's certainly true, yes. And then actually there's also the issue of the UV radiation not being constant. So you could maybe have a situation where there's flares that are impacting the planetary atmosphere, and then you have a time-dependent atmospheric response. So that becomes even more complicated, yeah.
Thank you.
Okay, so we have still some time for another question. So if there is nobody who would like to ask, so really also in the chat. Okay, nobody. So Robin, thank you very much again. It was very nice and very, very informative talk. And thank you for coming, and see you next time. So have a nice day.
All right. Thank you very much for hosting me. It was very nice. Bye-bye.